Hello everyone, this is Dilip. Today let's talk about unrolling and gradient checking in neural networks. So in the last video, we have seen about backpropagation algorithm and how we can use it to calculate the derivative of the cost function with respect to any parameter in the neural network. And once we have the calculation of cost function and calculation of the derivative using the backpropagation algorithm, we can use any optimization algorithm like stochastic gradient descent or Adams classifier or any other optimization algorithm to get our weights or parameters. Now let's take a look at the concept of unrolling. If we take a simple neural network as shown in the picture, as you can see in the layer 1, we have a 3x3 9 parameters. And if we add the bias neuron as well, we'll have 10 parameters. And in layer 2, we have 3 parameters. And if we add the bias as well, we'll get 4 parameters. Let's ignore the bias for now. And let's just use the neurons available in the network. Now, to represent all the parameters in layer 1, we need a 3x3 matrix like this. And to represent all the parameters in layer 2, we need a 3x1 matrix. And as you can see, we are going with multiple matrices at each layer. And if you want to do any vectorization or a simple calculation, it will be very hard because each layer is represented by a separate matrix. As part of unrolling, what we can do is we can take all these parameters in a matrix and put them in a single column. So here, all these, whatever you see in each column, you're just putting these first, and putting the second column, and then putting the third column. So this way, each layer of a neural network can be represented by a single column. And if we have multiple columns like this, representing each layer, then we can have a single parameter or weighted matrix available, and which we can use for our calculations, and that is much faster that way. So when we talk about convolutional neural networks in the later videos, you will understand more about this unrolling. So for now, let's move on. Gradient checking. When I was talking about backpropagation algorithm, I did not give all the details or exact pseudocode because backpropagation algorithm is tricky to implement and it can change with the given problem in mind. So that's the reason I did not give an exact pseudocode for the backpropagation algorithm. Now, how do we know whether backpropagation algorithm, whatever we implemented, it's working properly or not, whether its derivative calculation is working fine or not? What we do is, first I'll explain the concept of gradient checking. So at any given point in a curve representing the cost function with respect to parameter theta, how do we calculate the gradient at this point? What we can do is, we can go a bit this side, a bit this side. Say for example, this is epsilon. So theta will be changed by theta minus epsilon as well as theta plus epsilon. So this is the theta, and that is theta minus epsilon. And this point is theta plus epsilon. So what we are doing is we are decreasing and increasing theta by certain weight, which is epsilon. And then we can see how the cost function changes. So how the J changes when we change the theta. As I've already explained in one of my last videos, a gradient is nothing but change with respect to y-axis, change in y-axis with respect to x-axis. So here, how much j of theta plus epsilon and j of theta minus epsilon differ divided by the difference in how much this theta changes, that should give us the gradient. So this will be the formula for that. And as you can see here, theta and theta will cancel out, and this epsilon plus epsilon will be 2 epsilon. So this will be the gradient at any point. If we want to calculate, we already have a radially function available. So this is the derivative. And one point to note is here is the calculation of j of theta plus epsilon or theta minus epsilon is costly. That's the reason we go for gradient instead of directly using the cost function this way to calculate the derivative at any given point. Now, putting this into our backpropagation algorithm, what we can do is whenever we calculate the cost function derivative with respect to any parameter, then we can also do gradient checking for it, such that once we calculate the cost function at that parameter by 2 epsilon, which is epsilon is nothing but how much we are adding and subtracting the parameter. This can be any value you can put between 0 and 1. That's fine. So once we calculate that, we can compare with the derivative, and if those values are nearly becoming equal, it means whatever our implementation is there, it is fine. The backpropagation implementation is fine. And since calculating the cost function is costly, we should not do this multiple times. So for example, for a few iterations, along with calculation of derivative in the backpropagation function, we can put calculation of this value as well, and then keep comparing. And once both of these values almost like they look like they are converging, or backpropagation algorithm, we are sure it is fine, and then we can stop calculating this right side one, since it is costly to calculate. So that's how we use this gradient checking in neural networks. So thanks everyone for watching the video. Bye.